Chris and I do have a big announcement, and we try to do a drum roll. So we just have a imaginary drum roll here for now. But we have some exciting news to share. That is, we are writing a new book. So most of you probably are familiar with our first book, Data Science on AWS, and Chris can post the links here in the chat window. We're currently working on a new book, as you can see here on the screen, Generative AI on AWS, following our tradition. I'm super excited. Chris, do you want to share a little bit about the book?
I will share that I will never write another book again, but I said that after the first book, so we'll see.
Didn't we?
The other thing is the price just dropped by what was it, 64 cents. So yeah, get in now while you can.
All right.
Yeah, no,
so
we had a great time.
Yeah.
We brought in Shelby as a co-author. Yep.
Exactly. Yeah. So we have 3 authors now, Chris, myself, and a colleague, Shelby. We're targeting an end of the year release. We're trying to get it done a little bit earlier, but the book is already on Amazon.com for pre-order if you're interested. Chris will share the links in the chat. Super excited, and hopefully once the book is out, everyone loves it as much as we loved writing it.
And yeah, one more thing, we got permission to do full color in this book based on the success of the first book. So that's really exciting. We'll be actually color full images, and yeah.
It's a color book. Even better.
It's a color book, yeah. It's a coloring book.
All right. That was a quick plug. Super exciting to share the news. And let's come back to today's meetup. First, and I'll zoom in here a little bit. First, we'll have Vasily Vasinov. He's CTO at Griptape, who's gonna talk about dynamic rec with short-term memory. And just a quick intro, Griptape, for those of you who don't know the company yet. Griptape is part of the AWS Generative AI Startup Accelerator program. Chris, I think you are actually one of the mentors, right?
Yep.
So super excited to have them here today with Vasily and sharing a little bit about rec. You can never talk about enough about rec. So looking forward to learning more here about dynamic rec, short-term memory, and also a little bit what Griptape is doing in that space. And then second, our speaker is super excited as well to welcome Nikita Kozodoi. I hope I pronounced the name almost right. He is an applied scientist at AWS. And he will talk about detecting AI-generated text. So that's obviously a field that is very much in active research. And I'm looking forward to that talk to see what's happening in this field and hopefully learn about some techniques that are being discussed. All right. And with that, let's say take it away, Vasily. I'll stop my screen share here.
All right, great. Yeah, thank you for the introduction. So I'm Vasily, CTO and co-founder of Griptape, and today I'm going to chat about a number of things. So I'll first cover what Griptape is. At the high level, today it's an open source framework and a company built around that, but I'm going to only talk about the framework itself today. Then we'll cover briefly what RAG is for folks who don't know what it is. The previous webinar really focused a lot on RAG, and I'd recommend watching that to kind of get all the nitty-gritty details about that. After I cover briefly what RAG is, I'll go into what the challenges with RAG are and where it doesn't fit when folks try to use it in various scenarios. It's mostly conversational workflows with agents that need access to real-time data. Then I'll introduce the concept called dynamic RAG that we've been playing around with a lot internally. Then I'll finally get to the demo. So first, let me cover what Griptape is. Griptape is, as I said, a modular Python framework for integrating LLMs and other models with enterprise data and APIs. The way we differentiate the framework, and originally what we focused on, was minimal prompt engineering. So we kind of aim to keep all primitives to be accessible by regular Python scripting. And you still need to do some prompting, but we call it steering. So you don't need to write any prompts from scratch. And the second piece that is very important is that we try to keep all data that comes back to the prompt. Well, supposed to come back to the prompt. We don't push it back to the prompt. We keep it in short-term memory and let the LLM decide how to use it. So at the very high level, the framework itself consists of so-called structures, and those structures are basically a way to shape tasks. The simplest type of structure is an agent, which only has one task. And a task can really be anything. It could be question answering, summarization, chain of thought, many different things. A pipeline is a sequence of tasks that are connected to each other. And the workflow is basically a DAG. It's a way to represent complex flows, complex scenarios with multiple tasks that some of them can execute in parallel, some will be sequential, but ultimately they'll be executed as a DAG. At the high level, that's what Griptape is. And today I'm only going to show agents because they're the simplest type of structure, and that should be enough for what we're aiming to accomplish today. So let's now talk about RAG and what is RAG. So RAG stands for retrieval-augmented generation. It's a technique that was around for a while and was kind of recently rebranded after a paper came out called retrieval-augmented generation. The idea behind it is that first, the developer who wants to use this technique, they retrieve and vectorize data from an internal knowledge base, and then they augment the LLM query that the user provides with the data that was initially vectorized. So to make this more concrete, we can look at the high-level architecture of how that works. So this is how you could do RAG with Griptape. You first pull the data from a data store by using a Griptape loader. Then the Griptape loader generates embeddings, which is a way to represent textual data by generating vectors. Then those vectors go into the vector store, and they just sit there, and kind of you can update those embeddings, or you can query for those embeddings. There's a variety of different techniques of how to pull out relevant embeddings. So, for example, if you have a text, you can split that text into chunks and then vectorize individual chunks, store them in the vector store, and then when the query comes in, that query will pull out only the relevant chunks, or the top n number of relevant chunks. So then when a user makes a request to a Griptape client, the Griptape client first pulls out relevant, the Griptape agent pulls out relevant information by hitting up the query engine. The query engine gets pre-processed data from the vector store. The relevant chunks from the vector store are returned to the query engine. And then finally, the Griptape agent can hit up the LLM with the original request and the relevant text composed of the relevant chunks from the vector store. And this allows for much more precise results for the LLM to generate, because LLMs, as we all know, have data cutoff at certain dates, and if you just ask a question about some thing that happened recently to the LLM, you go to ChatGPT, and then it says that it has a knowledge cutoff. So with this technique, you can augment the original query with up-to-date knowledge, and the LLM will actually use that knowledge to answer the question. So now, what are kind of the issues with RAG that dynamic RAG addresses? So with when you use RAG, there's a number of things that are problematic. The first one is data processing costs, and here we're mostly talking about operational costs that emerge when you pre-process data. Those operational costs include the issues with the actual vectorization, with the pipelines that you have to set up for vectorizing data, because the data could be structured and unstructured. It could come from a variety of different data sources, could be SQL, could be just a bunch of PDF files from an S3 bucket, but ultimately you need to operationalize it. The second issue is those data sources are ultimately static and are limited by what was originally pre-processed, which again is quite useful for certain use cases. For example, when you don't want the LLM to go into, like if you don't want the LLM to do things on its own, right? So you only want to ground the LLM in very specific data, in very specific knowledge, that works fine. But what happens when you want to get more stuff that the LLM didn't originally have access to? So that becomes an issue. And the third problem is that data can become outdated that was originally vectorized, and that kind of connects to the first point of having to pre-process the data and having to operationalize it and make sure that the data doesn't go stale. So how do we address it with dynamic DAG? With dynamic DAG, data is vectorized and cached in real time. And we take advantage of the technique called chain of thought for that. Only the most capable models on the market are can really achieve that. So GPT-4 and Claude 2 being the two of the most prominent ones, but you can do that with off-the-shelf open source models as well today. So by using chain of thought, we can prompt the LLM to use tools to pull out that data, but that data doesn't have to go back to the prompt, and oftentimes that's actually not a desirable outcome. Because that data can blow up the prompt if you go over the token limit. So that is an issue with really a lot of data sources. For example, if you try to query a website, that website can have a lot of information on a specific web page, and if it goes back to the prompt, you either have to cut it or it blows up the prompt, and the API, the model API returns an error. So this like just-in-time vectorization works great for small data sets. It doesn't. It's not small in the sense that it's tiny. So it can obviously work with megabytes of data. Doesn't work for terabytes simply because it takes quite a bit of time to vectorize it and store it. But works great for a lot of tasks that conversational agents can be useful for. And the third point about dynamic RAG is that it enables some of the off-prompt patterns, and I'll talk a little bit more about off-prompt once we get to the actual demo. So at the high level, the way we implement dynamic RAG in the framework is outlined in this architecture diagram. So there's no data pre-processing. The client goes directly to the Griptape agent. The Griptape agent prompts the LLM with some chain of thought prompts, including the so-called react, or reasoning and acting. tech prompts. So it provides a list of tools and a list of capabilities to the LLM. Then the LLM decides what to do for a specific request. And if it needs to use a specific action, the chain of thought action, it uses a Griptape tool that was injected into the agent. And then that tool executes something. For example, if it's a web scraper, which I'll cover in the demo, it goes, picks up content from a web page and stores it. Instead of returning it directly to the agent, it stores it in memory. And memory, what it does, it processes that output, dynamically vectorizes it and puts it into a vector store. And as a return value, it gives a memory pointer back to the agent. And then the agent, depending on what the current context is, decides what to do next. It could be querying that data that was returned from that was stored in the vector store. It could be passing it to another tool, or it could be summarizing it or extracting data in a certain way. By here, say, it makes it decides to query that specific bit of data that a tool returned. Then it goes to the query engine, it queries it, the vector store returns relevant chunks, and then it can do the same thing that it did in the previous example in the regular reg. The point here is that the data is live and it doesn't have to be pre-processed. So this should become more apparent once I start on the demo, which is the next piece. We're going to look at some code here. So I'll do two quick demos right now. So the first one is an agent that uses two tools, the web search and the web scraper. The web search is just a tool that performs Google searches, returns some results, and the web scraper is the one that picks up content from a web page, and that content doesn't go directly back to the prompt. It goes into memory. So everything is automatically connected internally inside of the agent. The user can specify all those different things, like connecting memory to tools, disabling memory, and a bunch of other things. But here, so let's run this example. So again, to quickly show what's happening here, we have a web search tool, we have a web scraper tool, we have an agent that has two tools injected, and then we have a little chat utility that wraps an agent and starts a chat. So here we can start talking to our agent. So maybe we can ask something like, what's the latest from npr.org? And here we can see the logs for the chain of thought that is going to happen. So I'll first walk through this really quickly. So the thought that the LM has is to find the latest news from NPR. It can use the web search tool to search for the website, and then the web scraper tool to get the content of the page. So it searches for npr.org to make sure that this is the correct website. So these are Google search results, and we're returning those directly back to the LM because we know that those are not going to blow up the prompt since there are only 10 of them here. Then the LM decides that the first URL is the official NPR website, so then it decides to use the web scraper tool. It hits up npr.org. And the first interesting bit here is that the output of the web scraper doesn't go back to the prompt, it goes back to memory. And so what Griptape returns is the pointer to that memory. So it has the memory name and the artifact namespace. The artifact namespace is basically a pointer to the collection of artifacts, which are bits of data that are returned by tools. So in this case, the web scraper returns a single text artifact, which is the content of the web page. Then the LLM figures that it needs to do something with that. So it goes into memory directly and asks Griptape to summarize that specific memory, that specific data that the pointer is pointing to. Griptape summarizes it, so it gives some information. The text is from NPR and includes top stories, yada yada. So basically, all the latest stuff. Something about potential impact of climate change on poison ivy, and this is the final response from the LM that would go back to in the chat to the user, and then we can keep chatting with it, asking things like, what is the potential impact of climate change on poison ivy? And in this case, again, the agent will probably go and search Google for the result and kind of do the same thing it just did. We'll pick up the web page, then go to, so it looked at Google results. I imagine it will go to the first result to scrape the content from that web page, and then it will go and summarize it, since the content of the web page went back to memory and only the memory pointer was returned. So it actually uses the query now instead of the summary. And the query answered the question pretty well, I would say. So this is a very, very simple example, kind of a basic example that uses dynamic reg. And again, dynamic reg in this case is the ability to augment the initial prompt with data that comes in dynamically depending on the context. The other cool example of what can be done with this technique is passing data between different tools. So this is a slightly more complex example. So we can actually disable those two tools and only focus on the tools that are relevant here. So here we have a file manager tool, which allows the LLM to read files and write files on disk. And the tool output processor is a way to kind of do what you saw in the previous example, where memory was accessed directly. The query and summary actions on the memory were accessed directly, but here it's in the form of a tool, meaning that the output of the result of the query can go back into memory as opposed to being returned directly to the LLM. But for this, for the first example here, we don't even really need to use that. So we'll just focus on the file manager, and here I'm just going to run the agent. I'm not going to chat to it. I'll just ask the question, give me a summary of the file attention abstract .txt in the files directory. And attention abstract is just the abstract of the attentions all you need paper. So this is a super quick example. It will go use the load the file from that directory. It will go and summarize it later. So kind of the same thing that we just saw, but this is the first step of what I was gonna show. So here it used the file manager tool. It read the result. Again, the Griptape returned the pointer to the memory, and now the LLM decided to use the summarize activity of the memory to summarize the content of the file, which a lot of us have already seen probably since it's the attention is all you need paper. So now let's do something more interesting. We're going to look at the case where we should actually let's do this. Let's summarize the file the way we did it before. And well, you know, I'm not actually going to modify what I had here so it doesn't break during demo. So here, I'm gonna leave 3 tools in place. So we have the WebScraper, the file manager, and the tool output processor. And here I'm asking Griptape to summarize our website and store the summary in this file. And as we go through the chain of thought, notice that none of the content ever hits the prompt again, ever hits the prompt, the main prompt. So we can follow it. We can follow the full chain of thought loop here, and we'll see that the data that comes back from the web scraper, again, goes back into memory. The next step, the LLM uses, instead of using the memory itself to summarize a specific memory location, it uses the tool output processor to summarize it. And the summary from the tool goes back into memory. So now it's been a two-step chain of thought that happened. So it now lives in this artifact namespace. And finally, the LLM uses the file manager tool to store the summary from this memory in the file. So it used the file manager tool to create this file. And so here's the summary of our website that was scraped in real time. And again, the important thing here to notice is that at no point did any of the data was returned back to the prompt, neither the initial data nor the summary itself. So this is one of the patterns that dynamic DAG really enables in Griptape, is the ability to enable LLMs to move data around without actually ever seeing the data itself. And this example concludes all of my demos, and I'm done. I'm ready to answer questions if there are any.
Thanks so much, Vasily. And I also want to quickly welcome and introduce Kyle here. Kyle is the founder of Griptape. He joined, and I put him here in the panelist too. And Kyle was answering a ton of questions already in the chat, so thanks so much, Kyle. Also, if you want to jump off on the mic or video, feel free if you want to. Let me go through, I know we have a bunch of more questions coming in here, super interesting topic. Let me just summarize maybe a couple of that were important. I don't think we have answered yet. We had a bunch of questions around embedding models. Are you aware of any benefits or better quality results with different embedding models for your own data? Questions around, does it help to fine-tune an embedding model, add knowledge, experiences with the right vector length, etc.? So do you have anything to share around that?
I don't really. I think for in terms of embeddings, that's kind of like it's been an easier problem in general for everyone to solve. And from our experience, embeddings provided by top companies like OpenAI and Anthropic and even smaller models are good enough for most things. Like, we haven't run really into issues around querying relevant information from vector data stores that came down to just the quality of embeddings. Like, sure, in certain cases, like in highly specialized texts or in interestingly formatted texts, that could become a problem, but I wouldn't say that it's a bottleneck. So okay. I think in general, if it does become a bottleneck, if the quality of responses is not great, I would just encourage to experiment with different embedding models, because that likely means that the shape of the data is structured in an unusual way. So that just needs to be experimented with.
Okay. And then also a little bit on, I guess, the bottleneck questions. How does this work at scale, Griptape, with managing a large amount of pointers in memory? Any issues with garbage collection, etc.? And then also maybe a follow-up for the memory. Can we use in-memory low latency databases like Redis or DynamoDB?
Yeah, so not garbage collection is interesting. I guess you really need to talk a lot to the agent for this to become an issue. I think the idea is, again, like, and I tried to call it out, and I'll repeat this again. This works really well for small data. So think conversational agents, kind of like personal assistant type agents that don't need access to, terabytes and terabytes of data, because vectorizing that in real time becomes a challenge. And that's why you do want to start to pre-process that type of stuff. In terms of those vectors being cached. So I think that's something we do. So effectively, if say you ask the LM to answer some question about a PDF, so that PDF needs to be processed the first time. Well, once it's processed, it sits in the vector store, and it doesn't have to be pre-processed again because of how we do it internally. So in this sense, it becomes efficient at that level. In terms of like managing those pointers, so there are two dimensions to the issue. The first one is doing that in the context of a single session. If it's a single session that you're talking to the agent, during which you're talking to the agent, you have the so-called like conversation memory. That's kind of like the memory that has nothing to do with the tool memory. It's the memory of all the interactions that you've had with the agent so far. And that could get tricky, because if there are too many of those pointers that were returned and kind of stored within that memory, that eventually overflows the LLM. And so a different approach is needed. For example, storing those pointers in yet another data store and letting the LLM query that data store for relevant pointers to the data. But that almost becomes a different tool or a different entity within Griptape. And the second dimension of that problem is, so I think, well, probably what the original question was trying to address with the garbage collection, like if it ever becomes an issue with the actual like computer memory. So I don't think that becomes an issue, because again, the data is too small. So I know I just answered like probably 3 different questions.
No, that's perfect. Thanks so much, Vasily. All right, in the interest of time, I think we have to move on, but there's a ton of more questions in the chat. Vasily, if you have a little bit more time to spend, maybe help answer those. And Kyle, thanks so much for already answering a bunch. You put on here the website and the GitHub link, right? If people want to reach out, what's the best way? Just via the GitHub repo, or?
If they want to reach out with questions, so we'll have a Discord server which is available. Like the link is on the website, as well as the GitHub repo. You can reach out by email. It's just Vasily@griptape.ai or Cairo@griptape.ai. If that's a better way. Otherwise, yeah, submit issues. Try it out.
Perfect. All right. Thanks so much. Really appreciate your time on the presentation today, Vasily.
Mm-hmm.
And
thank you.
Yeah, let's see what's coming there soon. Excited. All right. And with that, we're switching over to our second speaker, Nikita. Thanks so much for joining us. And we're going to learn how to detect AI-generated text. Take it away, Nikita.
Great. Thanks so much. Let me quickly share my screen and let's jump straight into the topic. Just quickly confirming if you can see my screen well.
Yes, we can see it.
Great. Right. So hi, everyone, and thanks a lot. Very happy to be here. I'm an applied scientist at AWS Generative AI Innovation Center, which is a team at AWS which works with customers looking at helping them enabling their generative AI journey, identifying and implementing different generative AI use cases. So we have a couple of open positions. So if you find this topic and other generative AI topics interesting, feel free to apply. But the thing that I want to talk about today is the detection of the AI-generated text. And this is the topic of research and exploration, which me and some of my colleagues has been looking at in the past couple of weeks and months to see what is out there. So now I would be happy to share my learnings and findings about this topic. So I plan to talk about a couple of things. First of all, just explaining why detecting AI-generated text is important. And then we will quickly look at some of the findings about the linguistic comparisons of the generated and human-written texts. And then, of course, the most interesting part is to look at the different approaches to detect generated text that are available out there that people have came up with. And if we have time in the end, we'll also talk about different techniques to actually evade those detectors, which sort of puts us back to square one in the task of the generated text detection. Before we start, just as a quick teaser, I invite you to quickly read those two texts on the slide and maybe paste in the chat which text do you think is real. Just maybe put one or two in the Zoom chat because I'm very curious to see what would be the distribution and what do you think, which text is real or which text is generated here. I'll just give you a few seconds. So I'm looking at the chat. I think we have more votes for the first text being real, but also I see quite a lot of messages saying that text number 2 is real. But it's maybe 60% for the text 1 being real and 40% for the text 2, judging from my quick look. Well, the real answer is that the second text is actually written by human. And I saw that some of you noticed that the first text actually has a typo. Well, the language model was instructed to make a typo in this text. So this is why it was very difficult to understand what the right answer here is. And I think this is also a very good illustration to why this topic is very important. And as expected, it is not as easy to actually tell those texts apart. So let's chat a bit about why is detecting generated text important. If you look at some reports and some news articles out there, you will see that there are different opinions stating that a lot of content in just a few years from now, a lot of content in the internet will be AI generated. You may or may not believe those exact numbers, but it is clear that the volume of the generated text increases every day. And what makes things worse is that we, as humans, we are not very good at actually detecting which text is real and which text is generated, as we just saw on our small example in the beginning. So the screenshot on the slide is from one of the papers who actually conducted a study on people trying to interrogate each other and realize whether they are talking to a human or whether they are talking to a language model. And as it turns out that even after interrogation, so even after being able to ask a couple of follow-up questions, only 68% humans could guess correctly whether they are talking to a human or whether they are talking to a language model, which is not a great number. And we should keep in mind here that people were having this opportunity to actually ask a couple of follow-up questions. But what happens if you only see the text and you also not able to actually follow up? And trying to trick the bot into answering using some certain patterns, it makes things even worse. And this task of judging whether the text is real or not, you could think of many business applications out there where this is becoming very and very important. For example, you could think about the task of removing fake product reviews on e-commerce websites, or you could think about detecting plagiarism in different assignments, be it student assignments, be it some exams, be it some other essays or blog posts or articles that journalists are writing. So a lot of applications where we are dealing with some text written by a human we should be able to judge whether this text is coming from the human actually, or whether this text or part of this text has been generated using a language model. So what should we do? Well, let's first of all have a quick look at the texts. So some of the researchers out there have studied the outputs of the language models, have studied some of the data sets where language models are producing answers, and real people are producing answers as well to a certain set of queries. And the researchers were trying to compare what are the typical differences between the texts, the answers that are coming from the language models, and the answers that are coming from real humans. I put a couple of diagrams on this slide from one of such studies, and you can see the title of the paper here in the bottom right corner. Looking at these diagrams, the panel on the left compares the sentiment of the generated texts between the human responses and ChatGPT responses. And I think what is really can be noticed from this diagram is that there are far more neutral texts coming from a language model, and not so much on the extremes of the sentiment. So this is the first finding, that the most of the time typical texts generated by a language model turn to be more neutral and less emotionally emphasized. Another finding that is coming from the same paper is that the looking at the parts of speech that occur in the texts, you could also see some differences. For example, you can see that the generated texts tend to have more nouns and more verbs, but less of some other parts of speeches. I did truncate the tail here, but there were also many on the right side. So what it tells us is that the texts generated by a language model tend to be more factual, more stating different things, and less emotional again, right? Because we're using nouns more frequently. So that means that the text is more argumentative, exhibiting sort of informativeness compared to a typical human. So there were many diagrams and many analyses like this made, but summing up this study and some of the other studies as well, the key bullet points that we could arrive here in terms of the differences are that apart from being more neutral and expressing emotions less frequently, notable points are that language model responses tend to be more strictly focused on a given question. And this is very interesting because actually given a question, we humans tend to not only answer this question, but also wander around a little bit and talk about some things that are maybe not directly related to the original question, but still maybe relevant in our mind. And this is not something that language models tend to do. So they tend to focus more strictly on a given question. And you can read a couple of other differences on this slide, and happy to get back to this discussion afterwards. But for now, let's assume that we see that there are some subtle differences between the typical texts generated by language models and humans. So the question is, can we actually leverage those differences, or are those differences too subtle to basically do any detection, to do any classification of the texts into human written or AI generated? Well, this is where the research and the development on existing on the text generation detectors coming. So looking at the landscape of what is available out there at different approaches that people and organizations have came up with, we can broadly split those detectors into three groups: watermark-based approaches, supervised detectors, and zero-shot detectors. And we will touch on each of those approaches to see what are the differences between them and how they compare, and maybe in what cases some of them may be useful, maybe more or less useful. So looking at the first group, the watermark-based detectors, the key idea here is that given the output of a language model, we can actually manipulate this output to make it easily detectable, but still keeps the same quality of the text. So key idea, let's see how we can manipulate this text and actually plant some kind of a watermark in this text so that afterwards it is easy to judge whether text is written by a human or not. So there are a couple of approaches here, and one of the notable approaches that I think illustrates this idea very well is soft watermarking. The idea is as follows. When a language model is generating a text, it generates it one token at a time, right? So we're going, for simplification, let's say one word at a time. On each sampling step, when we are drawing a next word from the distribution of words, what we can do is we can actually alter the probabilities of different words. Let's say we have a certain list of green tokens, of green words. Maybe cat is on the green list and dog is not on the green list. And then what it means is that when we are sampling those words, one word at a time, we will assign a higher probability to the words from the green list. So a cat will feature more frequently in our responses than a dog. We can do those changes in probabilities very small, but if we apply them across the whole set of tokens, then given a large text, we will start seeing some typical differences, but we are drawing these green tokens more and more frequently. And then, of course, afterwards, we can just calculate, knowing what is the set of green tokens, we can calculate how many green tokens do we see in the outputted text and use it as a signal towards whether the text is likely to be generated or not. So this makes things very easy on the detection stage, because to run this comparison, you only need to have a list of words and quickly compare the text with this list of green tokens. And it's very accurate. But the problem is that, of course, here you are required to have access to the text generation pipeline. So you actually need to embed this watermarks on the sampling stage. So you need to have this access to the model before the user ever sees this text. Which means that if you don't have this access, then you are not able to actually use those watermarks. Let's say we don't have this access. Maybe we don't have the access to the sampling mechanism of the model, but we are still able to get between the model and the user. So we're going one step away from the model. Now we are not on the sampling stage. The model is a black box, but we see the text that is coming out from the model, and we can manipulate this text before the user ever sees it. This is where we can apply the so-called post hoc watermarking. So here the approach is, okay, let's assume the model is a black box, but let's take this text that is coming from the model, and then let's change it. Let's shuffle it around a little bit using certain rules before we show it to the user. And then again, knowing these rules, we can easily detect whether this text is likely to be watermarked, to be generated, or whether it is text that is coming from a human. And here there is not a single method to rule them all. There are a couple of rule-based and neural-based methods, which we'll not dive into, but the general idea is, let's take a text and let's try to paraphrase it, manipulate it in some way before we show it to the user. Again, we don't need to have the access to the actual sampling, but we still need to have access to the text generation pipeline, because we need to make sure that the text is manipulated before the user sees it. So this was great in these cases, but let's say we don't have any access to the model, right? Someone else might have used the model, which we don't have any control of, and comes to us and says that this is a piece of text that they have written. What should we do then? Well, in these cases, this is where supervised detectors come in. And here the idea is quite simple and straightforward. Let's just train a binary classifier that predicts whether the text is generated or real. And in order to do that, of course, the first thing we need to do is to collect the data set. So this comes also as a main limitation of this method. What we need to do, we need a large data set where we actually have pairs of observations. We can have texts that are generated by written by human, and texts that are generated by a language model. And we need to gather a really large data set to be able to train such a classifier. And of course, we can take one of the pre-trained NLP models, for example, Barth, and then simply fine-tune this model to solve this classification task, judge whether the text is real or not. Looking at the advantages and disadvantages of such approaches, what we see is that, of course, it doesn't require access to the model. it still requires collecting this data set, but this can be feasible by querying the language model many times and augmenting the real human data set with such answers. But what we see from the empirical results, and I would avoid showing you too many tables to not get bored, but what we see is that such classifiers tend to overfit to the training data, and especially to the kind of model they have been trained on. So what it means in the real world is if you train such a classifier on the output of model A, and then model B comes out next week, then the classifier is likely to do a poor job on detecting the text that is coming from model B. And now, of course, given that new models keep coming out very, very frequently, and the new models are typically getting better and better, you can see that this really turns into the race. Given that the new model comes out, can you quickly collect a large data set to train a reliable classifier? It may be challenging. And of course, not knowing which model a potential person might use to generate the text and then try to pass this text as a real text, it is very difficult to address this with such detectors. So trying to overcome the issue of having to collect this large data set, the research has also considered different zero-shot detector methods, where the key idea is to look at the text distribution and avoid training a classifier, but try to do this detection based on the text distribution. And there is one recent method that I would like to stop here for a minute and explain to you, because this is something that also sounds quite promising. So this is a detect GPT method which was released this year, and the idea here is that we can look at the log probabilities computed by the language model when the model is generating the text, and then having those log probabilities, we are changing the text input. So, for example, we have this text input example shown on the slide. Joe Biden recently made a move to the White House, you can see, and then we change certain words in this output. So instead made a move, we say moved. Instead of moved, we say changed, we say decided, we say something else. So we create a couple of variants of this paragraph, and then we score this each version of this paragraph by calculating the log likelihood of a generation model, for example, of GPT-3. And the idea is that then we can look at differences in the log likelihood between those variants of the text passages. And if we see a drastic drop from one particular passage to different variants of it, it is likely indicating that the text is generated, because the model sort of overfit. You can think of it as overfitting on the training data, so overfitting on the kind of passages that the model is generating, but then producing lower log likelihood probabilities for the variance of this text with slight changes. So this is also an interesting method and an interesting emerging group of methods here. But of course, as you may notice from my explanation, you also need to access the log probabilities in this case. So you still require some access to the text generation pipeline. So overall, it doesn't look very good. It means that we can have a good detection quality with watermark detectors, but we do require the access to the model. If we don't have access to the model, we can use supervised detectors, but we see that with new LLMs, it poses challenges to us, and we see that it performs not so good on the texts that are coming and describing different domains from the ones that we have been training our detectors on. And what makes things even worse is that it doesn't stop here, because the community is coming up with methods to actually evade text detectors and make things even more complicated for us. One of the easy but surprisingly well-working techniques is simple paraphrasing. What you can notice from this table is that one of the detection methods has 97% accuracy, looking at the emphasized column here, when we do watermarking of the output. But once we start using another model to do paraphrasing, or you could think once a human actually starts paraphrasing a text that is coming from the language model a little bit, those numbers drop substantially. And you can quickly get to something like 57% of the detector accuracy just by using some paraphrasing. This illustrates how difficult it is. And of course, another way is to get away with some prompt engineering, right? As I was showing in this example in the beginning, we can actually instruct the model to be informal, to make typos, to use emojis, which are typical signs of the human written text. And then it becomes very difficult to actually do any detection because all those typical differences start to fade away. So I think to summarize, we see that generated text detection is important in many applications, in many business applications where the text can be coming not from a human, but a human could pass generated text as the text that they are claiming to be written by them. And we are not doing a great job in this detection. And there was hope that some of the detector approaches out there could help us, and some of them show really good results in some specific use cases. But we also see that in general, this remains a very, very challenging problem, because with every new language model and with every new advancement in prompt engineering tactics and in paraphrasing tactics and some of the other text detection evasion approaches, we will also be in this in a race between the people who are trying to generate realistic text and people who are trying to detect whether the text is written. You can think of it sort of as a fraud detection example, where fraudsters would always come up with new ways to confuse the authorities. Here, the language model coming out with ways to confuse us, just trying to be more and more realistic. And we as humans also learn how to instruct them to be really indistinguishable. And this makes it a very challenging task, but also makes it very interesting to observe how this field will evolve in the future, and what would be the next steps in the research and in the space of model providers who might think about different ways to watermark their text outputs and to enforce this in some of the important use cases. Great. I think that's it in terms of what I wanted to talk about. If we have time, we'll be happy to take some questions. Otherwise, you can also contact me on LinkedIn, and we'll be happy to discuss about this topic in more detail.
Thanks so much, Nikita. Awesome presentation on a very exciting topic here and very important topic. I definitely learned a lot. We do have maybe just time for one or two questions here, but I want to quickly call them out. You showed in the beginning kind of the distribution, right, of the generated language versus like human generated. Question came in: if you increase the temperature, will the LLM tend to answer less strictly focused on a given question, right? So
exactly.
How much influence does the temperature and other settings have on this?
Yes, thanks. That's a very good question indeed. Temperature and also the prompt, so the actual instructions, have make a lot of difference here. In this article here, they didn't actually explore how the results differ. So they just fixed a certain meta parameter values and were not instructing the language model to be very creative. And already we see here some differences, yes, but as I was mentioning, as kind of adversarial attacks, when you start increasing the temperature, when you start instructing the model to answer in specific styles, in specific ways, then all these differences stop making any sense. Then you would need to look at a whole new distribution profiles. So it is not possible to just say, okay, the generated language will always be neutral, will always be informative, and so on. As a general rule, yes, but depending on the actual settings, you will have to figure it out yourself.
Yeah. And then maybe one more question around the green tokens, which I think is a new term and concept for many. Can you elaborate a little bit more on the concept of green token and how those are implemented?
Yes, of course. So I'm showing another slide from my appendix here. So let's say before we start generating the text, we come up with a certain algorithm how we should watermark the text, and we just take all the words in our vocabulary and we split it randomly into two lists, and we call one list list of green tokens and another list of red tokens, completely random. And now what we do when the model generates an answer, let's say the model has already generated, I saw a cat on a. And the model is thinking, what is the next token to sample? What we will do is that we will take probabilities for all the possible words that could come after this phrase. And for green tokens, so one half of our tokens, we will multiply the probability by 2, let's say. And for red tokens, we will keep it the same. I normalize it, of course, but let's say we just artificially boost the probabilities of green tokens. And then it means that after generating maybe 100 words or so, you will notice that green tokens are featuring more frequently in the output text. Like you can see here on the right side with no watermark and with watermark examples. You will just have these green words appearing more frequently. And now if you know the actual watermark, so if you know how this token distribution splits into green and red, you can just calculate those green tokens afterwards and see what is the probability that it is happening by chance, and what is the probability that this text is actually generated by an AI.
Nice. And I guess for people to learn more about it, probably the paper is a good starting point.
Yes, of course. So you can see the links to the 2 papers here on the slide, and they have a lot of explanations about different watermarking techniques. So please feel free to read more on that.
Perfect. Thanks so much. Chris, do you have anything to add? Otherwise, I think we're good to wrap up here.
No, yeah, I think that's awesome. Thanks so much to the speakers, and I guess, yeah, do we know what the agenda is next week, Antje? Or yeah, next month?
Shortly. We're gonna publish on Meetup. It's too many topics always to choose from, but we'll publish an updated agenda for next month soon.
Awesome.
All right. Thanks so much to all of our speakers, Vasily and Nikita, today. The recording will be posted on our YouTube channel as always. And with that, thanks everyone for joining today.
Thank you.
Bye.
Thanks. Bye-bye.
Bye.